Okay, this video will walk you through an example of the calculations for lab number 3, which is the lab on the mechanical energy of the center of mass in walking and running. You're going to get a Microsoft Excel file from your TA, which has the data for your lab group that you measured for this lab, and it's going to have 10 different sheets on it. You can navigate to the different sheets down here at the bottom. There'll be, among those 10, there'll be 5 for running and 5 for walking. And each one of those 10 sheets, whether it's for running or whether it's for walking, will have a full stride of data that you measured in that particular trial for walking or for running from your lab member when they were moving over the force plates in the lab for this particular exercise. So each one of those sheets will look like you see on screen here. I'm just going to walk you through one of them, but you'll do the same types of calculations for all 10 of those sheets here. Each one of them will look like this. You'll have 3 columns of data, a column for the time, a column for the horizontal ground reaction force, or GRF, and a column for the vertical ground reaction force. So those will have data filled in there. These other empty columns, D through L, columns D through L, those will be blank, and those are the ones where you'll want to enter in formulas to calculate those data. Okay, so you're given the time and the ground reaction forces, and you're going to calculate the kinematics and the mechanical energies of the center of mass. You'll also be given some other data over here on the right in columns N and O that you're going to need to use to perform those calculations in these empty columns here. So you've got the body mass of the participant, acceleration due to gravity, you've got the measured average horizontal speed while they were performing this stride, the measured average vertical speed while they were performing it. You've got the initial height of the center of mass at heel strike at the start of this stride at time equals zero there. For that, we used the height of the marker on the pelvis to approximate that. And then there's 2 things you're going to want to enter into here because you're going to need these values to perform these calculations. You're going to want the body weight of the person, which equals their mass in cell O1 times their gravity in cell O2. Okay. And then you're going to want the time step, and the time step is the gap in time between any 2 consecutive frames of data here. So you can see the time starts in the first frame at 0 seconds, and then in the second frame goes up to 0.001 seconds, and then 0.002, 03, 04, etc. So every frame or every time we measure the data, the time has gone up by 1 millisecond or 0.001 seconds. So our time step, or our gap in time between any 2 consecutive frames, is 0.001 seconds. I'm going to change my units on my body weight here, or sorry, my significant digits on my body weight here to just 1. So I think that's going to throw off the significant digits of my other calculations if I use it there. Okay, so I've got all my data that I need here, time and ground reaction forces. And then I've got my weight and my mass and gravity and time step and average speeds and all these things that I need to use these calculations. Now, how do we actually do those calculations? Acceleration in the horizontal direction. To get that, we're going to add up all the forces that act on the body in the horizontal direction. And those forces are going to add to the mass of the person times their acceleration in the horizontal direction. So if we sum up all the forces in the horizontal direction and divide by the mass, we're going to be left with the horizontal acceleration. Now, since we're ignoring air resistance and wind resistance here, we're just going to assume that that force is 0. There's only one force acting in the horizontal direction, and it's this horizontal ground reaction force. So if I grab that horizontal force and I divide it by my body mass in cell O1, that'll give me my horizontal acceleration. Now, for O1, for my body mass there, I want to go up to that in my formula bar at the top there and put a $ in front of the O and a $ in front of the 1. What that's going to do is it's going to cause it to, when I then fill that formula in, like that, for all those cells, it's going to cause it to, here it grabbed cell B2 and divided it by O1. Then the next one down here, it grabbed cell B3 and still divided it by O1. Then you can see it then grabbed B4 and divided it by O1, and then B5 and divided it by O1. Tagging cell O1, the body mass, with those $ causes it to always use that cell, or always use this numerical value in cell O1 to perform that calculation. Whereas for the horizontal force, the B2 or the B3 or the B4, it's always grabbing that force at that particular time step that I'm doing the calculation on. Okay, so it's causing it to kind of increment the force there as my time moves up, but then to always divide it by that same body mass rather than moving down the row here and dividing it by things that are not actually the body mass. Okay, similarly for to get the vertical acceleration, we're going to sum up all the forces in the vertical direction and divide that by the body mass, and that's going to give us the vertical acceleration of the center of mass. Now, this is a little more complicated than the horizontal direction because there's two forces acting in the vertical direction. So I'm going to sum those forces up, and that's my ground reaction force minus my body weight. Okay? And again, here I'm going to want to stick dollar signs in front of my body weight because that's not changing. I want it to always be subtracting that body weight from every one of these ground reaction forces here on the left. Okay, so then that's my summation of forces. I'm going to divide that again by my body mass, and I want it to always use that body mass, so I'll stick the dollar signs in front of there. And then carry that all the way down, and I get my, my vertical accelerations. Okay, now I've got my accelerations, and I'm going to integrate those accelerations as functions of time to calculate my velocities. The formula for that, the formula for doing numerical integration, is in the lab handbook under chapter 3 here for lab 3. And to implement that formula, for example, if you want the velocity here in your second frame of data, that's equal to your velocity in the previous frame, which we don't have a value for, but don't worry about that. We'll cover that in a second. Plus 1/2 times the time step, which I want to put dollar signs in front of because I want it to always use that time step, times the sum of the current horizontal acceleration plus the most recent previous horizontal acceleration. Okay. And then enter that in there. And it says that it's 0, but it's actually not 0. We'll work with that in a second. Then similar thing for vertical velocity. That's going to be equal to my previous velocity plus 1/2 times the time step times the current vertical acceleration plus the previous vertical acceleration. Okay, we did not have initial values here for my initial horizontal velocity or my initial vertical velocity. Let's just arbitrarily set those equal to 0 now. We know that's not right, but we'll fix that later. And then let's calculate these velocities for all my time steps there. Okay, then knowing my vertical velocity as a function of time, I can also integrate that to calculate my position, my vertical position as a function of time. And that's going to be, again, using that numerical integration formula. That'll be my previous, most recent position, plus 1/2 times the time step, times the sum of the current vertical velocity plus the previous vertical velocity. Okay. And we again do not know the initial position, but we'll set it to 0 for now. Okay. Just to prove to you that these aren't actually zeros, I'm going to change my significant digits there to something a little bigger. So you can see there are actual numbers there. The position is indeed actually changing, and the velocity is indeed actually changing. They're just kind of small changes when we have them in units and meters and meters per second here. Okay, now knowing my velocities and my position, I've got everything I need to calculate my kinetic energy and my potential energy. Okay. My potential energy, that one's pretty easy. That's my body mass times my gravity times my height, which is my position, my height above the ground. And I want it to always use that mass, so dollar signs, and always use that gravity, so dollar signs there. Kinetic energy, that is 0.5 times my mass, dollar signs, times my horizontal velocity squared. And then I need to consider the kinetic energy in both directions, the horizontal direction and the vertical direction. So it's also going to be plus 0.5 times the same mass, and then times the vertical velocity squared. Okay. And then carry that all the way down. Okay. Now, the problem here is that I needed initial values here for my initial horizontal velocity and my initial vertical velocity and my initial position. What these are, like physically, is the velocity and the position of the body's center of mass at time 0 here, which is the instant of a heel strike of the right leg for this particular stride of data. I know that my height isn't actually initially 0. I'm some height above the ground at heel strike, and I know my velocities aren't necessarily 0 at that particular time. Okay, so I haven't assumed good values here for my initial velocities and my initial position. Initial position, initial height above the ground, we're going to set that equal to the height that we measured for the center of mass. So we'll just set that equal to the 0.9. Okay. And then for my initial velocities, those are a little bit more complicated. I don't know for sure what these initial velocities should be, but I know what the averages over all these time steps of all these velocities should be. I know in the horizontal direction, they should average out to 3.5. And in the vertical direction, they should average out to negative 0.03. Okay. So let's just see how close we are there by assuming zeros for my initial horizontal velocity. My average of that whole horizontal velocity column is some fairly small number. And then my average in the vertical direction is some number. Okay. So I don't know for sure what these initial velocities should be, but I have a pretty good idea that they shouldn't be 0, because when I put in zeros there, I get averages of velocities that are nowhere close to my measured, known average, horizontal speed and average vertical speed. So I'm going to fuss around with this initial horizontal speed to get it to equal the correct average for the horizontal speed. Okay. So since my average is 3.5, let's just try 3.5 there. And that actually got me pretty close. Let's try 3.51. That's me a little too high. Let's try 3.505. And that's pretty close there. Right now I'm at 3.50, and my average should be 3.50. Okay. Same thing here for the vertical direction. This one's a little bit harder to kind of like intuitively figure out what it should be. So let's just try 0.1. And that made my average go up, and I want it to go down. So let's try negative 0.1. That's still a little bit too high, so negative 0.2. Now we're getting somewhere. How about negative 0.3? That's too much. How about negative 0.25? Getting better. Negative 0.24. Almost there. Negative 0.23. Pretty close. How about negative 0.225? A little too slow, negative 0.226, negative 0.227, and that's pretty darn close, right? Negative 0.03, and if I round this one, then I get also negative 0.03. Okay, so that's the way that you want to settle on these initial values for vertical velocity and horizontal velocity. Calculate the average of the whole column when you assumed 0, and then put that average, next to your measured averages, and then adjust these initial values manually until your calculated average is close to your measured average. Okay, and how close? Well, get 2 decimal places there correct, and then that's close enough for these types of calculations. Okay, that gives me my actual kinetic and potential energy of the center of mass, and so let's generate a scatter plot of those things. So I'm going to graph time here. And also grab my kinetic energy there. Okay. I can go to Insert, Chart. XY scatter. Let's bring that up a little higher here. It's going to take a while. I'll just cut it. Oops. Paste it up there. There we go. Okay, this is kind of an ugly chart. Get rid of that title there. I've only got my kinetic energy on it. I want to also plot my potential energy. So I'll go to Select Data. And then let's add first let's give this first one a name. That's kinetic energy. And the second one we'll call that potential energy. And for x's, that's going to have time. There we go. And for y, it's going to have potential energy. Okay. Okay, so that gives me my kinetic energy in the blue line and my potential energy in the orange line. The line here looks a little funny, and it's kind of hard to resolve the values of them. You know, it doesn't look like they're fluctuating too much. In reality, they should be fluctuating. So let's kind of fuss around with this graph and make it a little bit more clear what we're looking at there. First, let's get some titles on the graph. So I want a primary horizontal title and a primary vertical title. Horizontally, I've got time in seconds. And vertically, I've got energy in joules. I don't like this gray, tiny font that Excel uses by default, so I like to change that to a black font with a little bit larger text, and I like to make these bold here. And let's make my graph a little bit bigger there. Here we can kind of see some fluctuations. You also have a lot of wasted space down here. You know, we don't really need to start this at 0 since the data don't approach 0. So I can change that by clicking on my graph and clicking on my axis, going to Format, and Format Pane. And there I can set my range here, my bounds on that axis. And it looks like I don't need anything below about 400 or above about 650. And so there I can start to see some of the fluctuations in the kinetic and the potential energy a little bit better. If you want to see them really well, like see them kind of plotted on top of each other, that's where you can work with these last two columns here, where I called it delta KE and delta PE. The delta there means that we're going to calculate how the kinetic and potential energy are fluctuating relative to whatever their values at heel strike were. Okay, so how do we get that? Well, we just take whatever is my kinetic energy at heel strike and subtract it from all these other kinetic energies. And similarly, I take whatever is my potential energy at heel strike and subtract that from all of these other potential energies. Okay, and that gives me my change in kinetic relative to whatever it started at heel strike, and change in potential relative to whatever it started at heel strike. And that'll be nice because you'll see when I adjust the graph here, then these curves will fall on top of each other better, and it'll be a little bit easier to kind of see subtle differences in their fluctuations. So delta KE, that's going to be my current kinetic energy minus my kinetic energy in my first cell, I2 there. And potential energy is going to be my current potential energy minus my potential energy in that first time step, J2 there. And then do that all the way down. And then I will adjust my graph here. If I click on the orange line, I can drag PE over from actual PE to delta PE. And then I can grab my blue line and move that from actual KE over to delta KE. Problem there is now I'm outside of my range there. These are more around 0 or plus or minus about 20 joules or so. So let's go back to here and change the range again. Let's set it to minus 20 and plus 20. Let's see what we got. And that's pretty good. Actually, we can go, looks like we only need to go up to about 10 or so. There we go. Okay, so there it should be a little bit easier to kind of see the subtle differences in terms of the change of the kinetic and potential energy. So to look at parts of the gate cycle where they're going up and down at the same time, or where they're going up and down in phase or anti-phase. So these are the types of calculations that you'll do on each one of these trials, all 5 for walking, all 5 for running, calculating the kinematics of the center of mass, and then the energetics of the center of mass, and then making a graph for each one of those trials, showing the changes in kinetic energy and the changes in potential energy during that particular stride of walking or running, whatever movement it might happen to be.